Legacy software, often written in C or C++, is the foundation of our most critical systems in both the commercial and government sectors. Many of these systems struggle to meet today's higher standards for security, speed, and performance. As a result, the Department of Defense has a critical need to be able to modify, update, and maintain legacy software with code that is more secure or provides new functionality. As part of DARPA's vSpells program, Galwa developed 3 tools, Taphos, Walrus, and Oxide, to help modernize legacy codebases by incorporating model-based engineering practices, enabling safer updates with machine-checkable guarantees and streamlined certification. Our process begins with a legacy codebase that needs to be updated. This often shows up as a tangled mess of C code, which is difficult to understand, may have security vulnerabilities, and is challenging to modify. To accelerate human understanding of the legacy codebase, we use Taphos, which is designed to recognize patterns in a domain, analyzing the code, and creating an interactive visual model of the functions, components, and relationships for a domain expert to explore. Once the target program has been analyzed, the Taphos-generated model can be used to identify and extract components and interfaces that need to be upgraded or modified. This process can be performed repeatedly and automatically on current and future versions of the system to capture the evolution of the target program. Next, we use the Walrus co-compiler to lift the pieces of C code identified by Taphos into more high-level and compositional SCADE and Lustra models, where it can be patched, modified, or maintained at the model level. At this point, users have 2 possible paths forward. Either they can use SCADE for immediate compilation, generating DO178C certified memory-safe C code, or they can use our Oxide tool as a more robust continuous assurance option. Both options generate memory-safe compatible C code that can be reincorporated back into the legacy codebase with improvements and modifications intact. The key difference is that Oxide verifies that every compilation step preserves memory safety. It does this using type-checking techniques heavily inspired by Rust. This allows code to be rechecked for security properties after it is compiled and after it is linked into a complete system. This also gives Oxide an edge over Rust-based compilation. Whereas Rust prevents many memory-related errors in the initial writing of code, once compiled, Rust code can still be compromised if linked to unsafe components. By contrast, Oxide's continuous assurance approach ensures safety not only when the code is generated, but during compilation and after it has been reintegrated into the legacy system. In short, Galwa has developed a cohesive toolchain that allows users to lift C code from a legacy codebase, automatically generate a model for easy analysis, modify or upgrade discrete blocks of code, and easily slot the modified code back into the legacy system for higher security or improved performance. Equipped with these tools, users can treat legacy codebases as modular systems, upgrading them incrementally over time, all while benefiting from a greater understanding of their codebases and the peace of mind that comes from continuous, provable correctness. Now that we've looked at the big picture, we'll explore each tool in more detail. First, we demonstrate the Taphos tool. This demonstration of Taphos will use sample integration with VS Code that we have developed. Taphos tooling can also be used in a standalone manner and even automated in a CI process. When working with legacy code, it can be difficult to get an understanding of that codebase, how it's architected, what subcomponents exist, how they interact, etc. Taphos can work with a maintainer or SME to help analyze code. Already we can see Taphos provides an overview of functions, and for each function the global variables which that function accesses and the other functions it calls. However, Taphos can also decompose the existing code into modeling components, which increases understanding of the code as well as providing a path to applying model-based engineering practices to the legacy code, even if it doesn't have existing models. Taphos identifies components by coupling user-provided hints with internal inference techniques. Here, the user suspects this codebase might use a message bus, so they look for functions that might send messages on the bus, and those that might receive messages from the bus. This information is captured in an instruction file provided to Taphos. Tafos will then be instructed to infer components based on the assumption that the components will communicate on the bus using these functions. Tafos identifies each separate component that receives a message, performs various actions, and then sends a response message. 5 different components were identified in this codebase. Each component has a group of member functions which now allows the user to think of the application in higher levels of abstraction. Tafos can then output those components to a model expressed in the AADL modeling language, which generates models of this existing code. Note that Tafos needed minimal information to generate a credible and useful model of this code. And now that the instructions to Tafos have been captured in this separate file, the analysis can be performed as needed during future development and CI processes to ensure that the model is always accurate with respect to the code, where the code is the ultimate authority of truth in determining what is actually deployed. This is the Visual Code Studio we're developing to serve as a front end for Tafos and integrate its results into DVS Code UI. Here's the message bus example loaded in the VS Code. The first step in this extension's workflow is to invoke the compile project command. To generate bitcode into the module to analyze, using the build bomb tool, which wraps around a variety of build processes. This example just uses a basic makefile. After you have the bitcode, you open the TPL script file you want to run Tafos on. This includes the command to look for a message bus style component. When the script is open, you invoke the run Tafos command, and Tafos outputs its analysis files into a generated directory. When you can visualize that output by invoking the display Tafos results command. This view shows the list of program functions and the components that Tafos infers from them. You can select the component to highlight all the functions in it and click on a function name to jump where it is in the code. In the code, you can hover over a function to view its Tafos analysis results. Tafos also outputs its results in graph form. You can view the graph in this panel. Tafos can output a big graph for the whole module or a separate graph for each component. Walrus is designed to help transition legacy C code into domain-specific modeling language like Lustra or Scade. To demonstrate its use, we'll take on the role of an engineer responsible for patching and maintaining a temperature-controlled monitor. Using Walrus, they will lift key functionality into Lustra and Scade, focusing on 2 critical functions. The first function is the monitor, which adjusts a control setting 0, 1, or 2 based on temperature changes, representing cooling, maintaining, or increasing the temperature. The second function simulates temperature changes, increasing the temperature based on the control settings in external weather conditions. Normally, these 2 functions are encapsulated within a driver that runs them in a loop, but in this case, the engineer wants to add the driver in Scade's graphical interface. To lift this code into Lustra, we run the co-compiler with the decompile flag. Currently, our tool processes C-Lite code, but C code can be translated into C-Lite using the verified compcert compiler. The engineer uses our decompiler to lift the C-Lite code, generating Lustra and Scade files. Upon inspecting the Lustra file, we can see that the 2 functions have been successfully translated into Lustra nodes, one that adjusts the control setting based on temperature, and another that updates the temperature based on the control and input weather. The engineer can also import the Scade files into ANSYS Scade, where they will see a graphical behavioral model of the temperature monitor and simulation. This allows them to refine the simulation or add a driver that utilizes these 2 nodes. Our tool operates by solving constraints. Running the decompiler with the verbose flag reveals all intermediate steps in the process. The intermediate programs displayed by Walrus are solutions to these decompilation constraints, one for each decompilation pass. A key feature of the co-compiler is its ability to work in reverse. Since it solves constraints, we can query them backward, allowing the co-compiler to compile Lustre code back into C-Lite. In this process, the tool effectively runs in reverse and always produces either the original code or a semantically equivalent version. Oxide is a language and its compiler we designed to support higher assurance compilation of memory safe code. Let's see how the Oxide compiler inserts and preserves memory ownership from source to executable. This is a small Lustre program written in Oxide. It is a trivial Lustre node that accumulates the sum of its inputs, but it will suffice to demonstrate the complexity of the Oxide compiler. Once elaborated, all types have been inferred, and from this compiler pass onwards, all types will be preserved at every step. After the stream elaboration pass, all Lustre nodes have been compiled into a couple of regular Oxide functions operating over a mutable state. This requires the use of regions, Oxide's equivalent to Rust's lifetimes. While the original program did not manipulate these explicitly, as we compile the code, the compile inserts and then checks these memory safeguards. Finally, this is what the generated LLVM looks like. The details are unimportant, but notice that while the LLVM type system only talks about the pointer's types, our higher-level type system captures deeper properties. For instance, the fact that this pointer argument is merely a borrow of a value owned by the caller, rather than an ownership transfer. As such, a safe linker should only allow this function to be called by functions that retain ownership of this argument. Used together, the Taphos, Walrus, and Oxide tools form a cohesive toolchain that allows users to lift C code from a legacy codebase, automatically generate a model for easy analysis, modify or upgrade discrete blocks of code, and easily slot the modified code back into the legacy system for higher security or improved performance. Contact Galois to learn more.